So our next session is on ExaScale Computing. Our chairperson for this session is Dr. Vijay Bhatkar. Our other eminent panelists for the day are Dr. Krishna Saraswat from Stanford. He would be addressing photonics-based supercomputing. Dr. Nash Palani Swami from Intel. He would be addressing quantum computing initiatives at Intel and future directions. And also Mr. Jean-Marc Dennis from Atos Bull, who would be addressing European exascale and microprocessing initiatives. I'd like to request our chairperson, Dr. Vijay Bhatkar, to take lead. So
this is the last session, and it's good news that the day has been very packed and intense, and there has been so much of learning. We are back to the question we started at how to realize exascale computing. And the panelists are going to look at it from a different perspective. If you look at the day, one word that got most repeated, echoed all through the day, rather I would say chanted all through the day, there has been exascale. Exascale, exascale, exascale. And one way to realize your goal is to, I think in our culture, is to chant that. That is, people do that actually, to realize God, chant the name of God. So it appears to me now, and it really appears that we can actually realize, I think Dr. Saraswati will agree that I got convinced, which was a doubt, which is a maybe question mark, can we realize exascale of Indian design, Indian manufactured exascale system? And we have been discussing in TAC and chaired by Dr. Saraswat. This question has been there. But this workshop, this conclave, has really unequivocally answered that question, that it can be realized. At least I got convinced on that now. This is a great, I think, takeaway from this. Now, this factor, I never believed that particularly how to build the ecosystem for the hardware, when the discussions were going on, and when the panelists came about, strongly that we have the best, if at all any country has a chance to really have the best ability and infrastructure to build exascale hardware, that is India. And that was quite a thing, and I believe that. I trust that now, that this can happen. Now we really have to leverage that to have happen. Not only that, we can go to the chip levels also. And I think last TAC meeting, that people came out with some innovative designs for the next generation chips, which will be designed here, and at academia, and there will be innovations there. I never expected that could happen. But today we got that confidence as well, that if you have the designs, we can make it right here. And more importantly, that the industry is ready to collaborate. One thing I found, another thing which happened, people were not marketing. We were not just discussing the corporate world, that this is Intel, this is IBM, this kind of thing. Of course, we did describe our own capabilities some way, but they transcended beyond and saw that as a national challenge. This is a great thing, something. I see this one. So this has been in a way this one, but now we are going to discuss on the way to exascale, and we look at that. One thing is clear, that the current designs, current architectures, it is very clear to most of the people, we can realize 100 petaflop machines, no question. Current architectures will scale to 100 petaflop levels. And that we will be able to use these machines also, and that is a challenge. Of course, we have to see. There's an application challenge which we have to look at that. But beyond that, are there certain breakthroughs awaiting for us? What are those breakthroughs? Are there some disruptive thinking which are happening? And two factors which come, two technologies which not that they are not new. They are, one is photonics. I think Dr. Saraswat talked about right in the beginning about silicon photonics. We must look at very seriously. And another has been, of course, that we have seen for some years now, quantum computing. And there's another one which I have not discussed here, is the biocomputing. So we are going to look at in this panel, and we are going to do it well on quite extensively on these issues. The issue of photonics, and we need to consider that kind of thing. And we have a remarkable person who has devoted a lot of time on semiconductors and photonics and the integrated silicon photonics. That is Professor Krishna Saraswat from Stanford, who helped us really in the semiconductor project as well. So let's begin. I will not waste more thing more. One more thing I want to see, that kind of thing. I want to give a parallel here. And we have the European initiative simultaneously going on as we are going on. I would like to recall right in the first CDAC or the Param architecture, when we were designing way back in 30 years back, there was European initiative also. We really recall the coming from which we mentioned about it, the Transputer initiative in the UK, and also pursued in the France, and the Suprinum initiative in Germany. And they were there for almost parallel. Today also we have the same thing, and we'd like to hear from the European initiative, what is their plan, how they are building, can we collaborate? Some way can we collaborate? And we'd like to listen to them. So before that, I think Professor Saraswat, Krishna Saraswat, please, you can begin your presentation and let's learn about photonics.
Well, I'm the other Saraswat from the other side of the globe. There are lots of Vijays here, but two Saraswats will probably do equally well in contributing to this technology. So today I'll talk about emerging interconnect technologies for ExaScale computing. So this shows sort of a progress in the transistor technology. So what you see is, starting when I was a graduate student in 1970 or so, we constantly made the transistors smaller and smaller by scaling. We did nothing else, simply just reduced the size. And hence we reached almost the turn of the millennium. At that time, around 90 nanometer, we introduced, people said the life of silicon is over, but silicon has more life than the cat. So silicon germanium was introduced in the source strain to impart the strain and hence improve the performance. At 45 nanometer, high-K dielectric and metal gate were introduced. Now at the 22 or maybe 10 nanometer node, silicon FinFET has been introduced. And looking in future, at 7 and 5 nanometer node, germanium will be introduced in the channel. Going in future, we have a plethora of devices, the 3.5s, the carbon nanotubes, the 2D semiconductors, and the SpinFET, which will continue the progress in the device area. Now, I'd like to mention, somewhere in mid-80s, I had the honor of meeting then Prime Minister Rajiv Gandhi, and Dr. Bhatkar mentioned several times his interaction. He came to Washington, DC, and wanted to know my view on what needs to be done. So he asked me to put together a team, which I did, involving people like C.K. and Patel from Bell Labs, Pallab Chatterjee from TI. We put together a proposal, a vertically integrated outfit, and we called the end result of that was Desi PC. So starting from chips, from silicon to system. Unfortunately, he was assassinated, and that whole initiative died with the successive government. Today, we have an opportunity. Well, what happened around that time, another one of Stanford alum went back to Taiwan and set up TSMC. And that became the largest manufacturer of silicon chips today. Now, 3 decades later, we have an opportunity, not in the devices or technology, but in systems. Following the example of John Kennedy, who said man on the moon, which was one objective, but it developed a plethora of technologies which contributed to the American economy. So today we have a chance to get back into that race and make this as a mission, the supercomputing or exascale computing, which will generate lots of other technologies in hardware and software and education, everything. So that would be my first slogan. So if you look at the transistor technology, all the way from the very first transistor, so this is Moore's law. Everybody knows that today we are nearing 10 to the 10 devices on a chip. So what is the problem? Well, over the years, we have developed new structures, we have incorporated new materials in devices, and as I showed in my first slide, we continue to march on that path. However, the interconnect problem has become progressively more difficult. It is resulting in excessive power dissipation, insufficient communication bandwidth, and poor signal latency. So we really need to explore other possibilities to overcome that problem. Now, where are the problems? If you look at the frequency of microprocessors, around the year 2002, it started saturating. And since then, it has not really increased too much. Why has that happened? Well, if you look on the left side, the CPU power density has sort of pegged at something like 100 watts per centimeter square. We cannot remove more than that. So, and that's the reason we cannot increase the frequency of computing. On the right side, you see the switching energy. With scaling, the dotted line shows what should have happened because of scaling, but more recently, because we have not been able to reduce the power supply, and therefore the switching energy is not reducing commensurate with scaling. So what I'm going to talk about, following things, something about scaling limits of interconnects, then the technology for novel optical interconnects, and a little bit about 3D integration. So first thing would be the performance comparison of copper, carbon nanotubes, and optical interconnects. So about 16, 17 years ago, my group did this study, and at that time we thought 50 nanometer was very futuristic. So we looked at the power allocation to different parts of a 50 nanometer processor, and we concluded, if you look at the red line down there, that more than half the power can be attributed to the interconnects. The upper half of clock 28%, signaling interconnects 27%. More recently, Wilfred Hensch from IBM came to Stanford and gave a talk and concluded that 70 to 80% of total logic power is for communication. My colleague David Miller recently published a study. So the red parts are attributed to communication and the black parts are to logic. And what it shows is that for logic, our energies are in attojoule or femtojoules, but if you look at various communication, it starts rising from femtojoule to picojoule to nanojoule and even microjoules. So it's clear that most of the energy is spent in communication. And we heard earlier, many other speakers said the same thing. So now the data, the rise in data problem. So these are some statistics which I have collected. The YouTube users uploaded 72 hours of new video per minute last year. This year is more, I don't have the data. Skype users connected for 33 million hours per day. Google received over 4 million search queries per minute. In a study which was done at DARPA in America, one Google search takes about 1 kilojoule of energy, which is one AAA battery. Only 2% of the electrical energy was consumed, 2% of the energy was consumed by data centers, and it's rising. This year, I think the figures say 4%, and that's only US. So all over the world, there is a big problem. The applications in these require high bandwidth, low delay, and low power dissipation. So what is the problem of interconnect? There is this vertical yellow line. To the left of it is a long haul communication. And that long haul communication is almost all photonic, using fiber optic communication. To the right of it, rack to rack, board to board, and on chip is all metallic communication. The thing you should see is with the decreasing distance, the number of interconnect which is used is increasing from few thousand to few billions. So for few thousand interconnects in long haul communication, we use handcrafted fiber optic systems. To the right of it, we rely on mostly copper wires. So where is the problem with copper wires? On the left side, you see a cutout of a copper wire, which requires a physical barrier because if copper diffuses into silicon, it just destroys the devices. And it has scattering mechanisms both at the grain boundaries and the surface. So on the right side, you see results of our simulation. Resistivity of the copper, the bulk resistivity should be less than 2 micron centimeter. But because of surface scattering, grain boundary scattering, and the use of a barrier at small dimensions like 0.05 micron, the resistivity goes up to 6-7 micron centimeter, and the overall objective of using high conductivity copper is lost. So if you look at an old wire which was short and fat, in a scale technology, it will be long and skinny. As a result, the bit rate, the delay, and the power dissipation all suffer, resulting in poor performance of a high performance computer. So what are the alternatives? I think we can look at other electrical interconnects like carbon nanotubes or graphene, or perhaps you can use an optical interconnect, or perhaps in a system level, we can assemble those things using a three-dimensional system as shown in the lower part of this figure. So an electrical system on chip is the top one, which consists of a driver, bunch of repeaters, and receiver. Repeaters simply reshape the pulses so that a pulse can travel on a longer distance. Off-chip communication cannot have repeaters, so you just have a driver and receiver. By comparison, the optical interconnect, the black parts are very similar to what would be in a conventional metallic interconnect, but the red parts are the new photonic devices. So you take an input signal, the pulses which are shown in black need to be transformed to optical signals through the use of a laser source and a modulator, propagate them on a waveguide, and at the other end convert them back to electrical signals and feed them. So this could be on chip, this could be chip to chip, or this could be at the board level or long haul communication. The principle remains the same. Now, if you look at the carbon nanotube or graphene, the upper part shows good thermal conductivity. So graphene has roughly 2 orders of magnitude better thermal conductivity than copper. Therefore, and also the current at which it breaks down, the CNT and graphene both are much better than copper. And as a result, their use for certain applications may improve the performance of a supercomputer. If you look at the latency, which is the upper curve, and the energy per bit, which is the lower curve, the red lines are for optics, and the solid line is for copper, and dotted line is for carbon nanotube. So latency, the optics always beats the metallic wires. in terms of energy, more than roughly half a centimeter length, optics makes sense. Less than that, I think either carbon nanotube and copper will still be used. If we can develop the technology of CNT, probably makes sense. This is a pretty busy figure. I'm not going to describe, but on the lower vertical axis is the power density, on the right side latency, and the horizontal axis is the bandwidth density. And the green lines are for optics. So forget about everything else. It says optics gives much better power density and much better latency for long wires. These are centimeter long wires. What about off-chip? So Professor Karen Bergman from Columbia did a study where she looked at all kind of computers. So in this figure, the horizontal axis is double precision computing in gigaflops, and the end of it is almost exascale computing. So if you look at for the power, if you look at the vertical orange bar, that is for photonic I/O. So these are the power consumption simply by I/O, not the rest of the chip, simply by I/O. The green bar is using conventional copper I/O. The memory pin count is more mind-boggling. So the orange line is again, if I go back, these two ellipses shows the difference between the photonic I/O versus conventional metallic I/O. The conventional metallic I/O will need in excess of 10,000 I/Os for exascale computing. Photonics can reduce that to less than 100 I/Os through the use of multiplexing, WDM or some other technology. Now, we're talking about data centers. If something goes wrong in the back of the cabinet, this poor guy is immersed in the sea of interconnect, trying to fix them. This could be reduced easily to a bunch of optical fibers through the modern technology. So this would be the modern technologies. You take bunch of wavelengths, lambda 1 through lambda 4, you propagate them, combine them. Before that, modulator is what modulates them to give you the pulses, and at the other end, you use the photodetectors to detect those signals, convert them back to electrical signals. This was actually demonstrated at MIT by Professor Stojanovic in a hero experiment. So the left side, this was simply demonstrating communication between a processor and the memory, which is what is the bottleneck for a modern processor. So through the use of photonic links, which are shown as bunch of, I don't have a laser pointer, so I can't show you, but those curved lines. Oh, but it doesn't show on the screen. I was hoping my computer would be here so I could use see it shows here but not there. So anyway, so this was a hero experiment, 70 million transistors, 1,000 optical devices, and 2 million transistors in terms of memory. So another application, the clocking. When you start using multi-cores, clocking is the heart of the processor. And using conventional metallic interconnect, if you have a single clock generator, from there to the other parts of the chip, there is very strong skew and jitter. These vertical arrows show simply light coming to different cores of a multiprocessor. It should be possible to have all the cores fully synchronized this is an example of 64 cores, but any number of cores at the same time. So a modern supercomputer, again, from the point of view of Vladimir Stojanovic, shows all the way far right is the complete system, and then he shows different parts of the systems where photonic interconnect can be used for communication from core to core and from core to memory. So what we really need is the last two bottom lines. We need very high bandwidth density and very energy efficient systems, which will require monolithic integration of photonic components on silicon. So what is the technology we have on hand? Well, what we need is that the top line says we need cheap, available in large numbers. Remember the figure I showed that as we get closer to the chip, the number of interconnects is in billions. The technology has to be compatible with CMOS. Silicon devices themselves are a long shot. Nature didn't really make silicon to be a photonic material. Currently, we use 3-5 materials and bond them to silicon CMOS, which is what is shown on the right side. The upper part is silicon CMOS, lower part is 3-5 optoelectronics, and we just use bonding technology. It's the current process which is used for long-haul communication. It is expensive, it uses too many resources, the yield is very poor. But again, if we need small number, we can use this technology. Germanium, if you look at the right figure, the 1.3 to 1.5 micron wavelength shown in the green dotted lines, germanium sits pretty there in terms of its absorption coefficient. It has the right band gap for 1.5 micron. It is already monolithically integrated. As I showed you at 90 nanometer technology node, germanium was put in the source drain of MOSFET. So all the foundries, all the companies do have capability of growing germanium on silicon. That technology exists. Now, so what we have done so far to implement that system I am showing on the top, the various components of photonic interconnects, easiest thing was detector. So we grow germanium on silicon and make either an MSM or a PIN detector. Waveguides are easy. Lots of people have done that. More recently, by working with IMAC and a bunch of other outfits, we have also demonstrated very simple PIN modulators. The problem comes in the laser. So lots of work has gone on at places like MIT and Stanford and other places where we have tried to integrate 3-5 materials, but if you look at the left side, you start with silicon, you grow silicon germanium, and then you make 3-5 structures. It is possible in the middle and the right side, we show 3-5 based laser, but the technology is very complex and very difficult. So most optical systems keep an off-chip laser made in a 3-5 material and bring light onto the chip, which works again for long-haul communication, but won't really work for billions of interconnects on chip. So what are our choices? On the left side, we show silicon, and this is those of you who understand the EK diagrams. It's an indirect bandgap material. It will never emit light. On the right side is a 3-5, something like gallium arsenide or indium arsenide. It's a direct bandgap material. It will emit light. In between is germanium, which is almost a direct bandgap material, but indirect. But by straining it, we can bring the direct bandgap lower, fill it with carriers, and then it can be used for emission of light. What you see in the red and the blue lines there, that by putting enough strain, this material can be made a direct bandgap material. So this is a hero experiment which we have done. We started at Stanford, my students graduated, they went on to NTU, and we collaborated. And we made this structure shown on top. The Venn diagram is shown at the bottom. On the right side is shown lasing for the first time from strained germanium. The catch here is it works at, the middle figure shows that it works at 83 Kelvin, stops at 123 Kelvin. So our current effort is to bring the temperature of lasing to room temperature. And the current experiments show that we should be able to do that in the next 6 months. So just a quick summary of the 3D, which is what will be needed for ExaScale computing. So what is a 3D system? In the middle is a 2D system shown where chips are side by side. On the right side, those chips are stacked one on top of the other. So on the left side, if you see that by converting a single layer system to just 2D layers, two layers, we can replace a long horizontal wire by a short vertical wire. So the other thing is, if you look at the 3D system on far right, the chip footprint is reduced significantly. That's the technology which has made possible your cell phones to be so small. Furthermore, because the interconnect length is reduced, the resistance, inductance, and capacitance are all reduced, making it possible to get reduction in the delay and power and high bandwidth. Furthermore, 3D technology allows the integration of heterogeneous technologies such as memory, logic, sensors, optical I/O, etc. This is a hero experiment with our student Max Scholaker, who recently joined MIT as a faculty member. So that's from his PhD thesis. So going from, in the middle, it shows a 3D system which consists of first layer of silicon FETs, second layer of carbon nanotube FETs, third layer of resistive RAM, and fourth layer of carbon nanotube sensors. So this shows a 3D integration with ultra dense vertical interconnects, and you see subsequent magnification showing a real proof. It is not simply artist's conception. So this is the kind of technology which is needed for exascale computing in future. Now, there were questions earlier in the morning about heat removal. So one of our faculty members, Fabian Pease, developed this technology about 20, 25 years ago, where if you look at the far right, upper part shows a concept and the lower part shows the actual implementation. On the back side of a chip, you etch a groove, which makes like a radiator of a car. You push fluid through it, and that fluid can remove up to 1 kilowatt per centimeter square of heat. More recently, Ken Goodson and Tom Kenny, who are in the mechanical engineering department, have pursued that technology, which is shown in the lower part. In the 3D structures, for each layer, you can make these structures and remove a large amount of heat. They also looked at, earlier I showed you the heat carrying capacity of carbon nanotubes and CNTs. You can embed those in your silicon substrate and perhaps remove the heat much more efficiently. So future systems, in my view, would look something like this. There will be 3D heterogeneous integration of interconnects, devices, memory, bio devices, MEMS and sensors, photonics, and of course the heat transfer. What will that do us? So people have been talking about Moore's law, and they say Moore's law is over, finished. So this shows their view of Moore's law, that starting at 11 nanometer, no more. Well, that is good for the 2D batch. If you go simply packaging, by packaging chips one on top of the other, you change the Moore's law. If you go bonding, one chip bonded on the other, there are more vertical interconnects. And if you go truly 3D monolithic, like what I showed you in a figure, then you are faster than the Moore. And the example I would like to talk about is the 3D NAND, where they have incorporated 100 layers, companies like Samsung, 100 layers of a NAND cell in a footprint of 40 nanometers. And that's where I think the technology is moving. So I think to say that Moore's law is dead is totally ridiculous in my view. This is kind of a summary of technology progression. The far left top shows the bulk CMOS technology that has gone from bulk to strain to SOI to FinFET currently, and we are looking at germanium and 3.5 and perhaps other new devices. What we have not done is interconnect that stays copper and low K. So there, I think if we fast forward to the right corner, the optical interconnects and the nanotubes should provide impetus to go down to 2, maybe 3 nanometer node for which would be really needed for exascale computing. So I'm not going to go in the interest of time, skip the conclusion, which simply says that copper days are gone, CNTs are better than copper for short interconnect, optical links are for long on-chip links and certainly off-chip. 3D heterogeneous integration will keep the Moore's law going for a while and will make exascale computing possible. So, well, my group, I have to show up. And thank you for listening to me.
Thank you, Professor Saraswat, that amazing peep into the world of photonics, and you have shown us it's extremely important for NSM as well to see where is the future. And I must say that we are just beginning on this process. We need to study, and of course, your group has to get involved and mentor and guide us in this process. We can take some questions, but I think that's not a thing we'll not be able to finish. So we'll move on to the next presentation now, from photonics to quantum computing. I'm very happy to say that Dr. Nash Palini Swami from Intel has flown all the way really to share the directions for quantum computing, maybe at Intel, but generally everywhere. Cross. So without losing much time, so may I request Nash to make a presentation.
Good evening, everybody. Hopefully everybody is awake. No, it's been a long day. My jet lag is hitting me now, so it's a good thing for me. I'm up here talking and not sitting there, so I may have gone to sleep. So one of the reasons I came here was to make sure I can share some of what we're thinking in the future. I am giving a little talk on ExaScale computing at Jaipur, at one of the workshops. But today I was going to talk about leading the evolution of compute, and I was going to go into neuromorphic and quantum. I wanted to go into some of the things that we've been working at from an Intel Labs standpoint, and where we think the technology is, and when we can see something coming out in the future. Again, I'm not a quantum physicist. Okay, I look at it more from a system standpoint and how you can actually develop applications and actually take quantum computing into real application space. Okay, with that, I'm going to jump into the thought process which is going on within Intel. As far as exascale, I know you've heard about the US DOE presentations which are online. We are not talking about the architecture openly, but it's basically going to be a new microarchitecture that we're targeting in the 21 time frame for exascale, and we'll talk more under our NDAs on exascale, but this is actually going a little bit beyond exascale, but some of these things will give better than exascale performance for certain types of applications. Okay. All right, so this doesn't work. All right, it looks like the fonts are not working on this. But I just want to go into our research efforts, right? So we have a components research lab, which is looking at keeping Moore's law alive and making sure we're coming up with new structures. They're looking at novel integration techniques, such as what I'm going to call you Dr. Krishna, so I don't confuse you with Dr. Saraswat. But what Dr. Krishna talked about, some of those things are actually getting into production. I mean, you may have seen the announcement a month back where instead of using a 3D integration technology, we're using more of a Lego-like technology, right? Where we have an interconnect, and we're actually putting an AMD GPU along with our processors. Okay, we have a technology called EMIB, which allows you to create something like a Lego. Okay, so that's some of the stuff that comes out of a components lab, right? So they're looking at future structures. As we're getting smaller and smaller, now we're getting into nearly an atom, right? And things are going to change. 3D integration is one way to keep a lot of the things alive. EMIB technology is another way to keep things alive. Parallelization, heterogeneous computing. Quantum computing is a new thought process in this whole move forward. Intel Labs is actually looking at saying, hey, what can this do in the future in terms of applications, and what future product capabilities are needed? Okay, so it's anybody can come up with a qubit implementation, but the key is how do you take this and make it useful, right? Without entanglement, there's no use, right? So you got to entangle those things to actually get a real application. Okay. And we work closely with the university research, right? We just don't do this ourselves. We work with a lot of universities. We collaborate with them very closely in the complete stack. Okay, we work with Stanford, we work with Harvard, we work with pretty much all the top universities around the world. And as you can see, from an application standpoint, we have Intel Parallel Computing Centers. And we have a lot of them in India. We have CDAC, we've done with the Indian Institute of Science. The key is all these applications, these centers are just not targeted on conventional systems we're doing. We're looking at seeing how we can move into neuromorphic and quantum when we move forward, right? These centers are a base for us to make sure that we can get real applications going. Okay. So, this goes back to what Dr. Narayanamurthy has talked, and you've heard this theme going on, right? One of the things that with ExaScale, right, what we're doing in the US DOE and Argonne National Labs, it's just not about exaflops, okay? There is a 50x requirement for real applications. Okay, so now those application spaces is just not pure modeling and simulation, right? What has been signed up by Argonne National Labs is you have AI applications, okay? You have big data applications, and you have typical modeling and simulation applications. And it so happens those three things are the big three vectors which are driving Intel's business, okay? So one of the key things that we are making sure, Sita talked about an end-to-end solution. Today if you look at our artificial intelligence solutions, we're bringing to market a broad range of products, okay? We have Intel Xeon, which is used in 95% of most of the inference applications. Pretty much 90+% on training too. People do not know that. A lot of people use GPUs when they're doing training on a daily basis, okay? If you're doing training once a month or something like that, it's much better to use Xeons or even your PC, okay? We're coming up with a new product, which is Intel Nirvana, which is basically really targeted at these daily users, right? I'll openly say it's going to compete with GPUs, but it's targeted at AI. It wasn't a graphics chip, so it was targeted, bottoms up as an AI chip. The third one is an interesting one. I don't know how many of you know this, but that's a USB stick, okay, which you can put in your laptop and do inference. You basically build your training model somewhere else, but you use this, as a USB stick, okay? So you can do, cafe types of inference on that USB stick. It uses a visual processing unit, which is basically a smaller version of this one. This is used in drones. It's basically an edge device. So basically if you're trying to do inference at the edge, where it's really low power, that's a 1 watt, USB stick, okay? And then of course we have our Intel FPGAs, which is being used by several other companies. I don't know if Narendra is there, but you've seen several of the big companies using FPGAs for inference and training, okay? So we have today's artificial intelligence products, I think we have a roadmap to cover it, right? But let's look at the evolution of what is happening. Today's solutions pretty much do what you see on the left side, right? It's empirically driven. It can handle complex data. it's got high accuracy on smart data. Where it lacks is handling ambiguity, contextual reasoning, right? So an example that I'll give is usually, if you look at all the traffic lights that you have today, typically you program it with some kind of timing and all of them are connected. But what if there's a network which can reason traffic and put everything together and make sure everything is aligned, right? Today, that solution is not that. People talk about smart cities. Today, really, there's no natural intelligence kind of solutions, right? That's kind of where people are trying to come up with solutions. Today's AI solutions with training and inference are not really connected at real time, okay? There is no adaptation. That's where neuromorphic comes in, okay? And quantum will take it another step. So I'm trying to build the solution space here, right? Autonomous learning is a key thing of natural intelligence, where people are learning stuff automatically, right? Your kid is learning, when they're, by the time they're 2 years old, they've learned how to learn. Okay, your neurons are already, ready to go. Okay, so the first 2 years, is very important for the kids and your neurons to develop. It's where you're, automatically learning. Like, you look at two dogs and you say, hey, one is a German Shepherd, another is a Labrador, right? It's, those kinds of things where, we are really not there in computing today. Okay. So what is Intel doing in neuromorphic computing? We've been pretty quiet about it, but we've been working on it for quite a few years. Okay, it's been at least seven years since we started this at Intel Labs. I'm just going to go through this quickly. If you look at it, you can look at a few types of learning that people talk about today, right? There's the unsupervised learning, where you're really looking at pattern detection, right? You look at data pattern, then you figure out, okay, this is the pattern. Supervised learning is where you recognize the pattern, right? Where you basically say, you know what, go look for a dog or a cat or something like that. Then the self-supervised learning, where you have some pattern association, which is kind of, where you basically, it's a lot of the car industry is looking at self-supervised learning and trying to go into reinforcement learning. Reinforcement learning is where you're making decisions, and that's where it gets tricky. Dr. Narayan Murthy talked about Lego, in terms of data. When you get to reinforcement learning and decision making, that's a huge, that's where I think a lot of the car companies are actually looking at putting ethic committees in place, just because of autonomous reinforcement kind of learning which is happening, right? Where you got to make a decision on saving lives or minimizing the number of lives. You can't make a decision on, hey, you know what, that person is older than this person, right? So those are the kinds of decisions making that happens over there. Okay, so we're looking at all these things. One of the things that we actually announced is a neuromorphic chip called Loihi. I'll go a little bit into the architecture of this of the chip. It's a groundbreaking research test chip. Okay, we have silicon out. Next year, the first half of 18, we're actually going to put out a software development kit, and we're going to be working with the universities and trying to figure out how you actually use it. The cool part of a neuromorphic chip, which is different from what you see today in AI, is this chip can do training and inference at the same time. Okay? If you actually program it, right, the way that you're supposed to program a neuromorphic chip, it is going to be self-learning. Okay? It's like a real-time control system where you're learning, you're building the model, you're adapting. Okay? So this chip it's basically a PCI Express connected. This is the neuromorphic part of it. We call these little things there neurocores. I think I can find the button. I can't see very well. Can you see that? No, I don't see it. All right, okay. So these little round things are the neurocores. This has got a very, very high-speed, scalable neuromorphic fabric, as we call it. So if you look at a neuron, how many of you are biologists here? I'm not. But I've been taking crash courses on biology with my son, who's in his 4th grade, and he's been working on this DNA project. That's a good one also. It's very connected to neuromorphic computing actually. And one of the things that I had to comment is off the side to this architecture was, I think we should start off, the training at the school level, right? What is happening now is people are learning this type of technology starting from the 4th grade. Okay, so I think we need to do that in India too, where we get to start people early in terms of artificial intelligence, what types of stuff that they can do, right? So going back to this, you have what we call neurocores. We have this as a PCI Express accelerator connected to Intel Longmon cores. We call them the Pentium cores, basically. We believe we have the most advanced of all published chips to date in terms of a neuromorphic chip. It's got 128 cores. It's got 3 Lakemont cores, which is the core driving part to it. We have some programmable learning rules. The cool part of it is each neuron can connect up to 1,000 other neurons. So if you look at your human body, right, you have your central nervous system, your peripheral nervous system, and each neuron is connected, right, from the axons to other dendrites through the synaptic clefts, as we call it, to lots and lots of them. Okay, they're extremely low power. Okay, and that's the cool part. And they do stuff in parallel, and they do it with spiked pulses. Okay, so it's got what we call the neurocores. Each of these cores can connect to about 1,000 other cores. You can have millions of neurons, millions of connections, right, and thousands of neurons there. The novel design methodology is, it's all asynchronous, so it's extremely low power, right? We're trying to mimic the neural system of your human body, of how we do stuff, which is extremely low power, right? And we've actually validated a lot of the proof of concept algorithms on FPGA before we built this chip, right? The way it's pronounced, it's called Loihi, right? Loihi is a volcano right next to Mauna Loa, right, in Hawaii, and it's underwater and it's ready to emerge, okay? So that is really where this is our test chip. We really want to get the application developers working on it. We're going to publish an SDK. We're going to have white papers on how you can program this. It'll have very clear instructions on how you do it. The key part of this is you can build a chip, but you got to be able to program it and do it. We have actually created something closer, to the neural system with lots and lots of connections. So the amount of synaptic connections you can do is huge. Okay. So the way our human brain works, the way the neurons work is they send what they call spikes, okay, and this is really what they call a spike neural network, and you can see some animations on how the spikes are, sent to different neurons. Okay, so this is kind of what the chip actually looks like. Now, before I jump into quantum computing, I just wanted to give you a little bit about neuromorphic, right, and how it actually works, right? So when you look at your when your human brain gets, let's say you're looking at a cat. Everybody loves a cat. I like a dog. I'm going to say it's a dog. When you look at a dog, you're going to have your eyes sending these spikes to lots and lots of neurons. Okay, and all of them are working on it. Okay, and they have, through the multiple years of training, they actually have some kind of a spike, database, right, which they look at. And some of the neurons, right, will actually look at this. It's a discrete event kind of simulation which happens within your brain. Okay, so some of them actually will start looking at it and say, you know what, it's a dog, and some of them may say, maybe it's a fox, but they communicate this to everybody else. Okay, through the synaptic connections, and finally a decision is made on a dog or a cat, and depending on how well you've been trained through your life, you'll come up with the right answer finally. Okay, so the final decision is going to actually be made somewhere, in some neuron at some place. But this whole process will happen in this neuromorphic chip, and the programming environment will bring all this back to make a final inference on what it is. Okay. Again, the cool part of it is it's extremely low power, it's asynchronous, it's lots of neurons, and most importantly, lots of connections between the neurons. Okay. And then we expect this to get better and better. We believe that, if this is a statement used by our labs folks, right? If you're running in a marathon, we're probably in mile 2 of the marathon. We haven't announced a roadmap or anything like that yet, but you can think that this could be some kind of an accelerator, right? That could come up in 3-4 years. Okay, how is it connected to ExaScale? No, it does do operations very differently, right? In terms of if you look at an exaflop machine or exa tensor ops machine, it probably will be much lower power and give as or better performance, right? When it comes to a training plus inference, it's most importantly it's self-learning and adapting, right? That's how you'll have to start rethinking the way you do these algorithms. Okay, quantum computing. I've done a lot of education myself, right? Working with these guys on quantum computing, and the whole concept, goes back to the idea that there are like key concepts in quantum computing. It's very tough to get your handle around quantum computing, but if you go back to the several things that have happened in the 1900s, it probably originated with a lot of the formulas that Ramanujan came up with, okay, which is actually being used by a lot of these guys. But if you go back to the original issue, Max Planck came up with this explanation, to figure out this ultraviolet effect, which happened as you went through to greater wavelengths of light hitting a black object. You had different phenomenon which happened as you moved with greater wavelengths, and so Max Planck's theory, boiled down, and Niels Bohr came up with this theory about quantum mechanics, and of course Einstein, always called it spooky, right? And with that, the whole idea of quantum computing has like a few concepts of quantum mechanics in play here, right? Where the whole concept is if you have if you have light, right? It's made of photons, and the photons is really represented by a wave equation, right? But it also behaves like a particle at times, right? And the wave is nothing but lots of probabilities of what the wave can be once it happens something, right? So with that, there are 4 concepts that are very important over here, right? Which is the first concept is superposition, right? There's a concept of bits in digital arithmetic, right? By it's a 0 or a 1, right? So if you have a register, right, at any point in time, your register, if you have 3 bits in a register and it's 0, 1, 0, the value of that is 2. Okay, if you have 3 quantum registers, okay, each bit is a quantum bit, right? The whole concept is each bit, okay, is going to be 0 or a 1, okay? You never know what it is. It's like when you flip a coin and it's rotating, that all the time it's rotating, okay? So it's a 0 or a 1. You'll never know what it is until you measure it. So effectively, right, in quantum theory, you have those 3 bits, right, actually represent 2 to the power of 3, 8 states at the same time. Okay? So what does it bring? It brings nothing, actually, right now. However, there's this property in quantum theory called entanglement, right, which is really what you can do to those states. Okay? And once you give an input to these states, it gets kind of entangled with that input, right? So all these bits have to be entangled with each other, all these 3 bits. Now you have some use for 3 qubits, okay? So now you actually have, states and inputs that you can actually do something with it. You can have a 1,000 qubit machine, but if they're not entangled, they're useless, okay? So that is the whole concept of entanglement. There's the double slit experiment, and if you guys have a chance, go look at YouTube, and you'll see what quantum theory does to that, and you'll understand the principle of the wave equation, and why, a lot of people's explanation is, hey, you know what? It is really a probability of multiple states that that photon can be in. Okay. The last one is a very important thing, right? People talk about a 50 qubit machine and stuff like that. These things are very fragile, okay? And any noise, once you observe it, you're done, okay? And then you have to redo the stuff, right? So the observation of noise causes a lot of information. The quantum error correction is a huge topic, okay? So you use a lot of the bits, okay, in a quantum computer to actually do error correction. But error correction in quantum computing is not like in general digital communication, right? General digital communication, you add bits to the input and you can come back and say, okay, there was one error detected or two. Here you actually have to manipulate the states. You have to entangle those bits, okay? And then from the result, you actually have to figure out what the error is. So effectively, you don't have, a 2 raised to the 50 computer in play, okay? Because you use most of the bits to manage the fragility of quantum computing. Okay. So here's what it says, right? With 50 entangled qubits, more states than any possible supercomputer, 300 entangled qubits, more states than atoms in the universe. Okay. However, none of this can be used commercially. We believe that you need to be at like 1 million qubits, okay, to actually have a commercially viable system. Okay, that's where we need to get to. And the main reason is the fragility, where you can go into decoherence very easily, okay, in a quantum computer. And that's the last bullet there, okay. I'm just going to build this stuff here. So basically, if you look at where the concept here in quantum computing, at least from a HPC standpoint, is you have all possible inputs or all possible states, right? You transform or filter them. It's basically how the transformation is really the entanglement. And then when you measure the result, right, you come up with one result, okay? And you keep doing this, you can get multiple results. That's where it's very different from the normal way you compute, okay? You got to take all these multiple results and make sense of it, okay? And that is the difference in quantum computing versus the regular particle. So people have been working on different quantum algorithms. If you get a chance, read about Shor's algorithm or Grover's algorithm. Shor's is a simpler one to grasp, okay? But the whole concept, you got to think very differently when you build these quantum algorithms. So there's a lot of work which needs to be done there, okay? So if you look at 50 qubits, it's a proof of concept, right? 1,000 qubits, you can solve some small problems. 1 million qubits, that's where I think you're going to get into a commercial scale in terms of cryptography or machine learning. We're looking at, okay, that's where you'll get into a quantum neuron kind of effort, okay? And the advantages of quantum is really, now since you have 8 bits representing 2 to the 8 states, right? What used to be exponential order, right? Somebody asked a question on NP hardness and stuff like that, right? What used to be an exponential problem could be now a polynomial problem. Okay. So much powerful. If you can actually get a quantum algorithm and you can interpret the results coming out of it, to make sense of it. So this is what a quantum computer looks like today, right? You need to have an application, a software architecture, hardware architecture, and the actual qubit devices, okay? Now, I'm going to build this up right here. So what are we doing in terms of quantum computing? Again, we started off sometime in 2015 with QTech, which is out of Netherlands. It's like a collaboration lab between University of Delft and TNO. They are some of the experts in actual qubit devices and the whole software stack too. So we're working with other universities also, like University of Chicago, MIT, Harvard, on the compiler stacks. But quantum computing is useless if you can't build applications, right? You got to build algorithms, quantum algorithms, which is a very different way of thinking. You need compilers. Even a quantum computer will have a quantum assembly. Okay, so next year we'll publish a little bit more about this, of this stack. The most important thing is the control electronics here, right? So the qubits, I'll explain a little bit more about how we do qubits today, and you'll understand why that control electronics is so important. And of course, you need a qubit simulator, right? So you can simulate qubits on, on a conventional computer. Well, it'll take a lot of time. Okay, so qubit simulator is extremely important. I don't know if Jean is here. Jean can talk a little bit about what Bull is doing there too, right? Okay. There was some public announcement on it. So there are really two types of ways that we have looked at in terms of qubits. Okay, the first one is what everybody's doing, okay, which is superconducting qubits. It's a microwave circuitry, right, which everybody's comfortable with, but you got to run that thing at 10 to 20 millikelvin, which is like 250 times colder than deep space. Okay, and that's why you'll see what the quantum computer looks like, right? That's how we create the qubits. The other way we are looking at, right, which is we build those qubits. I'll show you what we have done in terms of an actual chip. We build that using our technology today. We can do that today, right? The second one we're looking at is, if this thing has got to go commercial, we think it's about a decade away, right? By the time you get to 1 million qubits, you need to do it in a way that it is commercially feasible, right? And something that we have a lot of knowledge about is doing spin qubits in silicon, right? Where the 0 and 1 state is basically represented by like a single electronic transistor, and the spin state is up or down, okay? And that represents your superposition, and then when you measure it, you can measure a 0 or 1 depending on the spin state. Okay, so we are looking at this on a 300 millimeter wafers today, right, with 14 nanometer technology. So what is the progress Intel has made, right? That's one of the things that we wanted to talk about, is what progress have we made. Before we go in here, right, one of the things that we are also working on is we build the actual silicon. The package is very, very difficult on this one, right? Because now you're putting it in 10 to 20 millikelvin refrigerator, right, superconducting, and the packages have to be developed in a way that these things don't crack and can actually work in those cold temperatures, right? So that is something that we do a lot of work on from our side, from the qubit side. Okay. So we started off with the resonator. We did a 6 qubit which looked like that, and we announced our 7 qubit array test chip, just a few months back. And I'll explain what the chip is and what those little things look like, right? Which looks like your cable connection, which is what it is, by the way, right? And then we have the 17 qubit array, which we announced also. Okay, that's where we are. We have established a fabrication and package process. We are looking at building a new chip every quarter, where we keep increasing the number of qubits. Okay, this is using the first superconducting microwave circuitry, right? So we'll get larger, we're targeting larger, chips. We're targeting 49 qubits, right, in the next 12 months. We're looking at the silicon spin qubits, right? We have qubit wafers in progress. We want to make sure we have the quantum algorithms in place. Let me just, sorry, I hit the wrong button. But the key thing we're also doing is, if you looked at the chip that we showed, we had all these little coax cables, right? So if you look at this, if you look at the system itself, right, you can imagine that it's a big box. Quantum computing is not going to make conventional computing go away. There's still a processor which is connected to this accelerator, which is the quantum computer. And you have all these inputs which are coming from outside this into this refrigerator, which is the coaxial cables. Okay, so we have about 40 connections coming into this 49 qubit thing. Okay, and they're all coaxial cables, and these coaxial cables are carrying these RF signals which are generated outside. Okay. Now that's a problem, right? Once you have these long cables, it makes it very, very fragile, right? You can easily go into decoherence. In order to do entanglement, you need to keep this noise free, okay? Only if you get entanglement can you actually get a quantum algorithm done, right? So that's what the cryogenic RF control chip is. So we're working on this chip so that we can actually move the RF generation circuitry, all this, the big rack, which is sitting outside, we're going to move it inside the fridge, okay? So, but we'll still have a lot of the measurement, being done outside. So once you measure, your quantum computing is done, right? Quantum basically says once you observe it, you're done, okay? Okay, so of course there are a lot of people who talk about multiverses and quantum teleportation and all that stuff, but all that is for the future. This is simple, computing here. So that's one of the things we're doing in the next 12 months also, is to figure out how we can move that circuitry inside, how we can actually get to a silicon spin qubit, and also start working on the stack in terms of compilers. There's a lot of open source stuff which is happening also on quantum assembly and stuff like that. Okay. All right, so I'm going to build this out so that people can get a grasp of what we are, trying to put together in our current products and the vision for the future, right? I think with neuromorphic, like I said, I think we are now leading the pack in terms of a test solution, for people to try out neuromorphic. Quantum, I think we are mile one of the marathon. Okay, so if you look at conventional computing, you have known procedures, right, and you generate answers, right? In deep learning, you have known answers, okay, and then you generate procedures with training. With neuromorphic, you have many procedures, right? Like your brain thinks, right? And then you adapt the answer with reinforcement. As your kid grows older, he'll be able to differentiate between a dog and a fox. As he gets a little bit more older, he can figure out a dog is either a German Shepherd or thing. It's all, as you adapt the answer of the reinforcement, right? Quantum, that's why you got to think very interestingly, right? The answers are superimposed, right? Just because of the states in there. They're all entangled in there. All the answers are sitting in those, 50 qubits. And you got to figure out, you got to select and measure the answer, and you have to do multiple experiments to actually determine what the answer is. Okay. In Intel's mind, right, I think the future is looking bright in terms of, for the whole industry, right, in terms of neuromorphic is, it's not too far away, okay, 3 to 4 years. Quantum is quite a distance away. A lot of work needs to be done, right, to actually make sure that you can, get this working in a cost-effective way. You're not going to see quantum computers on your cell phone, okay? The way we envision it, at least, is it's probably going to be sitting in a cloud for some time, right, where people can use it as some kind of a burst mechanism to go and use it. Neuromorphic, I can see it becoming an accelerator. Very easily it could fit into, once we have a thriving ecosystem and a software and application environment that people can develop applications. Neuromorphic is much easier for people to grasp, I think. Okay. So with that, I think computing is not gone, right? Dr. Krishna said a good thing about Moore's law, right? You'll still have 3D integration. We have Lego stuff. That thing is going to move, and you can use these new technologies to fit in there either that way or in a block. Okay. Thank you.
Thank you, Nash.